Next we have Simon Sundelin from Chalmers.
Thank you very much. So today I will present to you some of our latest research where we have been investigated time-correlated quasi-particle tunneling events in a 2-qubit device. So my name is, as mentioned, Simon Sundelin, and I'm a PhD student in the group of Simone Gasparinetti in the 22Q lab at Chalmers University of Technology in Sweden. And apart from looking into quasi-particles, we also look into quantum computing with bosonic modes, quantum thermodynamics, and other quantum-enabling technologies. So, as mentioned many times greatly during this session, quasi-particles in superconducting circuits is something that, unfortunately, all of us have to live by with one degree or another. And they occur because high-energy phonons or photons excite Cooper pairs, break them apart, generating two quasi-particles, which, if they're in the vicinity of a qubit, can cause errors, phase errors, T1 errors, and so on. So naturally, we would like to mitigate these as much as possible. We want to mitigate the tunneling over the junctions and also just the density in general. So to this end, one can turn to improved shielding, high-frequency filtering, or gap engineering, as we have seen. But unfortunately, we can also observe these bursts of quasi-particles due to ionizing cosmic radiation, high-impact events due to radioactive materials in the vicinity of the ship, or just strain release in the superconducting film of our ship. And what this results in is very bad for quantum computation purposes, because it has been observed that these bursts of quasi-particles can cause correlated errors between multiple qubits on the very same chip. That is of course bad because our error protection protocols, if one wants to apply those, relies on that the errors that we observe are uncorrelated. So naturally it becomes of interest to try to detect and monitor these quasi-particles and these quasi-particle tunneling events onto our qubits, because we want to better understand the source behind these bursts of quasi-particles in order to develop mitigation strategies so we can improve the coherence times of our qubits and also gain just physical insight behind the underlying physical mechanisms. So to this end, we can turn to two main platforms, I would say. One is microwave kinetic inductance detectors, and the other one, which is what we turn to, are charge-sensitive transport qubits, where you can monitor the charge parity state of your qubit through, for an example, a readout resonator. So in our group, a little while back, we turned to a slightly different approach. We still use these charge-sensitive transport qubits, but instead we couple them directly to a transmission line. And then by simply performing spectroscopy through this transmission line, we can very well observe these even and odd charge parity states. And if one then monitors one of these frequencies over time, we can very clearly see this trajectory type looking trace, where a shift from high to low or low to high then corresponds to a quasi-particle tunneling onto your superconducting island across your junction. So naturally, how do we improve this setup? Well, we add another qubit to the transmission line, because then we might be able to study things such as correlated quasi-particle tunneling events. And if you also add a TUPA, so a better readout line, we might also be able to resolve these bursts, which I mentioned before. Notably also, we have a very small footprint of these two detectors, which you can see in the micrograph over here. And just once again, you can clearly see these visible odd and even parity states. And what we then want to do is that we want to monitor one of these frequencies for each of the detectors over a long period of time and see what we actually get. And this is then a typical raw data example of what we see. With about 100 microseconds resolution, we see these very well resolved state trajectories for both of the two detectors. And interestingly enough, in some regions of these traces, if you zoom in, what you see are in fact a sudden increase in the number of quasi-particle tunneling events. And overall, we observed 3 distinct classes of such bursts, where the first one here corresponds to the uncorrelated burst, so a clear burst in one of the detectors, not the other one. So with that in mind, of course, one can go about doing some post-processing, extracting the background tunneling rate, which we here see lies on the order of a few hertz, which is quite low due to the different mitigation strategies that we apply. But interestingly, if we only look at the bursts themselves, we see a tunneling rate which is about 1,000 times larger than that of the background. And also the rates of that these bursts occur is on the order of 1 to 2 times every minute, which is quite comparable to what other groups, probably some of you here in this room, have seen before. So the second one is then naturally the correlated events. So you observe a burst simultaneously in both of the 2 detectors. So that naturally leads to the question, okay, can we construct some type of correlation function here? And yes, naturally we can do that. By computing the cross-correlation in the intensity, or the number of jumps occurring in a small window of time, we see a large degree of correlation between the 2 devices for a small delay time, while if we remove the bursts from the data sets, this correlation completely disappears, corresponding to completely Poissonian, uncorrelated events between the 2 devices. And then if we turn on looking at the duration of these correlated bursts, we see that they tend for both devices to last on the order of 7 milliseconds. So quite a long time, actually. Then finally, we have this rarer subclass of observed bursts, which are the offset charge shifting bursts. And those are events which occur simultaneously with a change in the offset charge, which we can observe as a sudden change in the state discrimination between the even and odd parity state. Because when you have a change in the offset charge, the even and odd parity state frequencies will either move further away or closer together to each other, thus changing our state discrimination ability. So that you can very clearly resolve here. Okay, you don't really see it there. Where we have a sudden change in the state discrimination at the exact moment that we observe this burst. And if you were to plot that in the IQ plane, that would basically look like the 2 states moving either further apart or closer together to each other. And then if one go about plotting the timestamps of these offset charge inducing bursts, together with the effective offset charge, which we observe during a long period of time, we see that these bursts tend to coincide quite well with larger changes in the effective offset charge. And then this is then quite consistent with the interpretation that we have some type of ionizing event which causes a local rearrangement of the charge, but at the very same time generates a large number of quasiparticles, which we then observe as one of these bursts. And we also observe that these occur between 1 and 2 times per hour, coinciding quite well, which we heard here before, with the cosmic radiation causing these type of burst events about once every hour. And also the correlated events of these ones occur about 0.4 times every hour. So with that said, we demonstrate this very small footprint method of tracking quasi-particle tunneling events in a superconducting circuit with very straightforward implementation and multiplexing. And we also deploy 2 of these sensors simultaneously on the very same transmission line and observe these 3 distinct classes of burst events. We have the correlated bursts, the non-correlated bursts, and also this rarer subclass of offset charge inducing bursts. Then naturally we can continue on with this to try to look into how we can improve these background tunneling rates, the burst rates themselves, and also our physical understanding of the underlying mechanisms. For an example, if we can build some type of spatial localization sensor using an array of these very small detectors. So with that said, feel free to approach me after the session if you want to discuss more. Check out the paper, and also in our group we're currently hiring, so you can reach out to us either through LinkedIn or from our website. So with that said, thank you very much.
Questions?
Thanks for the thanks for the good talk. Maybe I just missed the part during the talk, but so offset charge shifting always happen at the same time in the 2 qubits, or do you see the correlation, or it can happen randomly in 1 qubit and the other qubit doesn't happen?
Yeah, good question. So we don't necessarily see them always occurring on the very same time. So here are the different rates where we see for the 2 different detectors, detector 1 and 2, which occur, so only detector 1 sees about 1.4 every hour and 2 for the other one, and around 0.4, so that corresponds to maybe 25 to 50% of the total number of offset charge inducing bursts. You see it there as 0.4 times per hour.
Okay, thanks.
No.
Hi. Very nice work.
Thank you.
Do you expect the distance between the qubits to play a role in this? If you make them too far apart, maybe the correlations become less or more?
Yes, definitely. So if you look into the interpretation of how these bursts appear, you have the phonons propagating through the substrate. So for the start, the timing or the start of the different bursts will probably be different depending on the distance between the 2 detectors. And then also how localized these rearrangements in the charge will also depend then, so on the distance between the 2 detectors. So if there is a large change locally around one detector, that will have a greater impact on one compared to the other.
Thanks.
Thanks for the talk. In your first subclass of events that you call uncorrelated, where you've got a lot of switching in one and not much in the other, was that a typical event? Like, do you typically see events where you have lots of switching in one channel and just a little bit in the other?
Yes, good question. So actually quite the majority, or between if I remember, 47% in one detector, and I think I quoted it here, 73% in the other detector. Of all those bursts, we saw correlated events. So actually, we saw more correlated events than uncorrelated ones.
Thanks.
All right, let's take our speaker. Oh, wait. Sorry, we're going to take it off.
Last question. You did mention what kind of substrate you are using for this?
Silicon.
Silicon?
Yes.
Okay.
Great, thanks.